Dear students, in this lecture, we will introduce the concepts of regression and using some of the discussions that we had in maximum likelihood estimates, we would try to develop an intuition that what this regression is, what is parameter estimation, and how we can use maximum likelihood estimates to estimate the parameter of regression. So, some of you may be new to this field of machine learning and data sciences, so I will go step by step. But first of all, why we care about regression as earth scientists or earth system scientists? So here are three motivating examples. So first motivation example comes from the fact that when we talk about climate change, we know that average global temperature is related to the concentration of various gases, specifically greenhouse gases. And we say that if we know the concentration of carbon dioxide, nitrogen oxide, methane, or chlorofluoromethanes and CFCs, we can develop some relationship between this global temperature and these greenhouse gases and understand what is the contribution of each GHGs. So GHGs would be greenhouse gases to control the average global temperature. So we are inquisitive from two sides. First of all, given that we know the concentration of these gases in the atmosphere, can we predict what would be the average global temperature in a given year? Second is, can we understand what is the sensitivity of each of these gases on the temperature? That is, what would result in maximum change in global temperature? Would it be increasing carbon dioxide concentration by 1 unit or increasing methane by 1 unit? And if we can understand that relationship, we can understand the earth system really well. So this is one of the biggest motivation, that we need to develop some statistical relationship once we have observed the data set. So this is one straightforward example and a simplistic example. Second example could be in terms of a two-dimensional images. That is, we know that in for a given region, precipitation, it depends on various factors. For example, it may depend on temperature, it may depend on the pressure fields, it may depend on the wind direction, that is UVW winds. So this would be our U wind, this would be our V wind, and W wind would be out of the plane, or in vertical direction, and so on. And we want to quantify this relationship. Given that we know the measure of temperature, pressure, winds, and so on, can we determine what is going to be the precipitation at a given area? Now generally, when we talk about some of these predictors, which we call as X, and we want to predict Y, so basically these X are generally available at much coarser resolution. Here 2-degree resolution typically means that 200 kilometer, that is, we know some predictors at 200 kilometers, that is, these points are spaced 200 kilometer apart, and we know their time series, and we are interested to predict what would be the precipitation at much finer resolution. So what we can do, we can develop a relationship between point A, or this is point of interest which we say as Y, and A1, A2, A3, A4, and so on, and say that how Y is related to the vectors A0, A1, A2, and so on. And once we develop this relationship, we can develop high resolution projections for local predictants. These predictants are typically called as Y, and predictors are typically called as X, and tell what would be the precipitation and temperature fields at local scale. Similarly, going to a little bit more complex example, we are also sometimes interested in image super resolution when it comes to our systems. That is, we have a coarse resolution output from a climate model. As I mentioned, climate models typically give us an output at a few hundreds of kilometers, and that would mean that if 2 points are 100 kilometer apart, there is point A and point B. Given the resolution challenge that we have in setting up these climate models, we will essentially represent these 2 points, which are a few hundred kilometers apart, with same climatology. However, that may not be realistic when it comes to climate change adaptation and mitigation, and we need the finer resolution projections as discussed in last case, where we want this information to be available at a few kilometers, sometimes at sub-kilometers, that is less than 1 kilometer scale, or sometimes at tens of kilometers. Now the question is, we cannot develop we cannot run these climate models at finer resolution given the computational challenges and the limits in uncertainty of microphysics. So what we do, we generally develop a statistical relationship between these core scale predictors, and these predictors could be core scale precipitation field, pressure field, wind field, as well as elevation, with the fine scale output. So we have our original resolution at hundreds of kilometers. We pass it through some, so you can consider this entire block as some transfer function, and we are transferring this x through this transfer function to obtain our fine resolution outputs of precipitation, which is typically at a few kilometer resolution, which could be 25 kilometer square, or 25 kilometer by 25 kilometer, or 4 kilometer by 4 kilometer, and so on. So this is the intuition or motivation that where we can use this regression. Now I've been using this word regression, so let us look into the formal definition of regression, that what regression usually is. So we talked about that we have some target variable y, and we have some input variables x. Now this x could be univariate, that it could be just one single variable, or it could be a series of variable, or a vector of variables. So the statistical method that establishes the relationship between y and x. So the sole role of regression is to set something like y is equal to f of x, and determine what is the functional form of f that can explain or relate this independent variable, we call this as independent variable, with the target variable. And there are n number of ways to determine this f, but in regression our biggest concern is this: what is the functional form of y. So just to give you an example, one functional form of y could be as simple as y is equal to ax plus b, and here we say that the functional form of x is linear, because we are linearly transforming x to obtain y by multiplying by a and adding a bias term or an intercept term, which we call as b, and this we call as a linear regression. Now the simplest case, as I just mentioned, is a univariate linear regression, where on x-axis you want to predict temperature, you have predictor x, and you want to predict pressure, which is predicted, and you observe certain temperature and pressure, and you plot them as a scatter plot. And the idea of linear regression is to determine the best fit line, and we all often call that this best fit line as the y hat, because this is the estimate, and our idea is to estimate a line such that the difference of square of error is minimized. So our objective is to minimize the difference between ground truth and what this line is going to predict. So now, for example, this is our ground truth of pressure at a given temperature. So we say that this is y, and whatever our model would be predicting, so we fit a straight line, so this would be our y estimate, and this would be our error. So this would be our error. Similarly, for each point we can say that this would be error 1, there is almost no error at point 2, this would be error 3, this would be error 4, this would be error 5, and this would be error 6 for this simple example. And now you can clearly see the reason for square, because we don't want to cancel out negative errors with positive errors, and we want errors to be additive so that we identify the best fit line. Now our objective in case of linear regression, or in any regression for that matter, is to estimate a line that minimizes the sum of squares of error. That is, I want to minimize e1 square, e2 square, e3 square, and so on, or identify or minimize the expectation of difference between y and estimate of y, and that should give me the best fit line. So this is the one simple example of univariate linear regression. Now coming back to multivariate linear regression, I started with the motivation one, that is given that you know the concentration of carbon dioxide, methane, some chlorofluorocarbons, you want to estimate what would be the value of temperature, so you want to learn this function. And now here we are dealing with multiple predictors against which we are predicting the predictant, and hence this becomes a problem of multivariate, and we are assuming that the relationship between temperature and these predictors, again I will not confuse the audience, so these have to be predictors on this side, and what we are predicting is predictant. So in case of linear regression, we say that T is equal to alpha 1 concentration of carbon dioxide, alpha 2 concentration of methane, alpha 3 concentration of CFC plus some bias term, and the objective in multivariate linear regression is to determine what is alpha 1, alpha 2 and alpha 3. Now, and as well as beta if this intercept is not known. Now, one thing to notice here is that why it is called as a linear regression. It is called as a linear regression because here we can express temperature as linear combination of parameters. And one thing to note here is that these coefficients are generally called as parameters. So I am highlighting these coefficients which we often refer as parameters in the language of machine learning. So the objective is to determine these parameters, and we say that the problem is of linear regression if these can be expressed as a linear combination of parameters. Now one thing to note here, even if you say that the concentration, the temperature may depend upon the square of concentration of carbon dioxide or cube of methane, we would still say that this is still a problem of linear regression. Although we are dealing with polynomials, the problem, if it can be expressed as alpha 1 x1 square plus alpha 2 x2 cube plus alpha 3 x3 cube and so on, this problem still remains the problem of linear regression, because again temperature is expressed as the linear combination of parameters. Now then question arises, can we give an example of a nonlinear form? So the example of nonlinear form would be if we are expressing this temperature as some function of alpha 1 carbon dioxide plus alpha 2 methane e to the power alpha 3 times CFCs. Now you see that the parameters alpha 1, alpha 2, alpha 3 are still there, but we are not expressing them as the linear combination of, we cannot express temperature as linear combination of alpha 1, alpha 2, alpha 3. So we say that this is an example of non-linear regression, whereas this still remains the problem of linear regression. So next time you see the polynomials, you do not confuse with the order of x's. Always look at whether parameters can be expressed as linear combination or not. Now, what are the three main tasks that we do when we have to determine the regression function? So first of all, we have to determine what is the order. For example, how many terms to include, what type of model we should go for. For example, in previous model where we are saying that y is function of carbon dioxide, methane and CFCs. Now question may arise, is it a, what is the order of carbon dioxide we should take? Is it a square, cube or higher order of carbon dioxide? And similarly, what kind of predictors to be included? Should we just rely on carbon dioxide and methane and ignore the chlorofluorocarbons? So we have to choose a model and how many parameters we are going to choose. So again, as the number of predictors increase, number of parameters are going to increase, and the complexity is definitely going to increase. And in one of the later videos, I will talk about Occam's razor principle, that how to choose the optimal model. But right now, this is one of the tasks that we do in regression. That is, let us start with one typical model and try to estimate these weights. Now, as I said that we have to estimate these weights or parameters, please note that these weights and parameters are often used interchangeably. but the objective is to identify what is the value of alpha 1, alpha 2, alpha 3, and so on up to alpha n if you are talking about multivariate linear regression that would result in the best fit to the data sets. And then we have to make sure that we are not overfitting, because whatever we would be dealing in the context of earth and atmospheric sciences, we are typically interested in generalized linear models or generalized non-linear models. That is, our model is not only good for the values that has already been observed, but our model should also be able to work well. I am saying quote unquote well because we need to categorize what this well means on surprise data sets. So here is a simple example. For example, there are some points which we want to classify and we draw a line or a boundary that separates them. Now we can always draw when we have already seen a data, we can draw a line that neatly separates each and every point that from circles to crosses. Now you can clearly see that the problem here is we are sort of overfitting. There is no generalization in this particular model. For example, even if my point comes here, right now my accuracy during training is around 100% in classification. But if I get a new sample where I have a point somewhere here, which I say it is X, but now our model is going to classify it as a circle because we have overfitted our boundary or decision boundary to these points based on the training data, and we have to usually avoid that because we want a generalized model that would work on surprise data sets or unanticipated data set. Now finally, when we are dealing with samples, we are always dealing with hands full of samples, so we always deal with limited data. And whenever we have limited data, we will always have some uncertainty in estimates of parameters. And whenever this uncertainty is involved, we have to inform that what is the level or confidence we have in our decisions, and hence we will learn something about confidence intervals when we go into regression. Now there are two questions that we need to answer: how to choose that what is the best complexity of the model, and where we will use AIC and DIC criteria, which are information criteria. Again, we are going to cover them as we progress. And second is to determine the parameters. Now there are two approaches or two schools of thoughts that how we can determine these regression parameters. One goes with the frequentist approach, that is, given that we have observed some data, can we determine what is the value of parameters. And in this frequentist approach, we assume that parameters are the true value of the model, and we compute the point estimate, that is what is the value of theta 1, theta 2. Now if you recall that we talked about maximum likelihood estimate. Now maximum likelihood estimate, what we were doing, probability of observing a data set given some point estimates of theta, because we were taking theta 1, theta equal to, that is mean equal to certain value, variance equal to certain value, and explaining the probability of data. So there was no uncertainty involved with the estimate of parameter itself. So we said that this is a frequentist approach. Now please do not confuse anything that appears as probability of X given something as Bayesian, because Bayesian talks about the posteriori. Here we are talking about the likelihood term that we understood in the Bayes theorem. So whenever we assume that these parameters are the truth associated with the data and try to explain the data, we are generally talking about the frequentist approach. And another approach is the Bayesian approach. That is, we learn that probability of theta given that some x vector is observed can be written as probability of x vector given theta times probability of theta upon probability of observing the x vector itself. And when we are dealing with the distributions over the parameters, that is, we are interested in identifying what is the probability of observing a given parameter given we have observed some data, we are essentially dealing with the full Bayesian framework. And we, in Bayesian framework, we say that there is no eternal truth about parameters. Whatever we are observing is just a probabilistic state. Certain values of theta would have higher probability to occur, certain values of theta would have lower probability to occur. So we are not dealing with point estimate, but we are dealing with a probability distribution, and then we are typically talking about the Bayesian approach. Now in next lecture, we will look into the ordinary least square, that how we can develop an intuition for linear regression a little bit more, and then we will give some Bayesian inference to the linear regression before we really move into programming, because understanding these concepts will help us in neural networks and deep networks concepts. So it's important to get some understanding of the basics and mathematics behind linear regression.